guys. Today's experiment is chemical reactions. The report sheet for this one starts on page 97 of your lab manual. What you're doing today, you're going to carry out about 10, 15 different chemical reactions. They're very quick. They're quick little test tube reactions. And for each reaction you do, you have to give us a complete balanced equation. So if you look at your report sheet, we'll do number 3 here for you. Okay, first I'll show you the reaction. We give you the reaction in words on the report sheet. So the report sheet says silver nitrate. Here's your silver nitrate. Mix it with calcium chloride. You'll get your product, silver chloride and calcium nitrate. And showing you this one, we'll take our silver nitrate here. Silver nitrate is a solid ionic material, but it's been dissolved in water for you here. So here it is all dissolved up in water. We're going to add the calcium chloride, which is also dissolved in water. So 2 clear aqueous solutions, and as we mix them, you see how it almost instantly turns to what looks like white paint. There's our reaction, and you see that white solid at the bottom? That is the silver chloride. It is called a precipitate. So when you mix 2 clear solutions and suddenly it gets all cloudy, you get solid material, the solid is referred to as a precipitate. Okay, you saw the reaction between silver nitrate and calcium chloride. Now, completing your report sheet, what we want you to do here is for each reaction, you have to translate the names of the chemicals into correct formulas. So instead of saying silver nitrate, we want you to write AgNO3. AQ means it was dissolved in water. Instead of calcium chloride, we want you to write CaCl2. And again, that was also dissolved in water. So half of this report sheet is an exercise in naming chemicals or nomenclature, going from the name to the formula. So it produced silver chloride, which is AgCl. That was the precipitate. The little S means solid. So that was that white chunky solid that you saw. And the other product is calcium nitrate, which would be CaNO3 taken twice. And that one would be the aqueous. Now, half of this report sheet is taking these names, translating them into formulas. The other half is, once you have the correct formulas, we want you to balance these reactions. Balancing a reaction means you have to have the same number of atoms of each element, both on the left and on the right side of the arrow. Right now, it's pretty obvious this is not balanced. On the left side of the arrow here, I have 2 atoms of chlorine. On the right side, I only have 1 atom of chlorine. So to make this work, I'll have to use coefficients. Coefficients are the big numbers that live out front here. The thing I don't want you to ever do, guys, don't go down this dark path. A lot of people look at this and say, hey, I got 2 chlorines over here, so I'll just say AgCl2. Don't do that. This chemical does not exist. So don't write that. What I'm trying to tell you here is, don't try to balance your equations by changing correct formulas into incorrect formulas. To balance, all you get to do is play with the coefficients, the numbers that live out front. So, again, our chlorine's out of whack. We have 2 chlorine atoms on the left, only 1 chlorine atom on the right. How can I fix that? I'll put a coefficient of 2 out front. That means 2 units of silver chloride, which represents 2 atoms of silver and 2 atoms of chlorine. Now, 2 chlorines here, 2 chlorines here. When I did that, that threw my silver out of balance because I have 2 atoms of silver. Over here I only have 1. Oh, that's easy to fix. I'll put a 2 there. 2 units of silver nitrate. That just means 2 atoms of silver. Balances my 2 atoms of silver over here. This also gives me 2 units of NO3. And if you look over here, I have 2 units of NO3. So, completing this lab report, take the names, translate them into correct formulas. Once you have all your formulas correct, balance the equations. Okay guys, when we wrote these formulas, you might have noticed I rather seamlessly just said calcium chloride was dissolved in water, got the little AQ. Silver chloride I identified as a solid. How do you know whether something's aqueous or solid? The answer is, you look at a periodic table that has the solubility rules. So, how did I know that the calcium chloride should be aqueous? Well, generally soluble compounds. Anything that has chloride, bromide, or iodide will probably dissolve in water. So the calcium chloride was aqueous. How did I know the silver chloride was the solid? Well, this rule here. Anything with chloride, bromide, or iodide dissolves in water except a silver halide. So if this is silver chloride, or silver bromide, or silver iodide, then it does not dissolve. So the solubility rules can be used to judge whether a compound dissolves in water or not. Okay, now we're going to look at some acid-base reactions. First, we're going to show you litmus tests. Litmus paper comes in 2 different flavors. You have blue litmus paper and red litmus paper. And these are used to tell if something is either an acid or a base. So we have a piece of blue litmus paper here. We're going to add a drop of hydrochloric acid to it. And what you see is the blue litmus turns red. So if you're using litmus paper and your chemical makes it turn red, that chemical happens to be an acid. Now, over here we have red litmus paper, and I'll add a drop of sodium hydroxide. You should know from lecture that sodium hydroxide is a pretty strong base. So we'll add a drop of the base to the red litmus paper, and you see how that makes the litmus turn blue. So if something takes red litmus and makes it turn blue, that something happens to be a base. Okay guys, we're on number 3 here. we're going to explore what happens when you add sodium hydroxide to a solution of phenolphthalein. So, here's our large test tube with some water. We'll add 1 drop of phenolphthalein, just 1 drop of the phenolphthalein. Phenolphthalein is an indicator. So, in just straight water, it's quite colorless. In the presence of an acid, it's colorless. In the presence of a base, it turns pink. So that's our phenolphthalein. We're going to add a drop of our base, our sodium hydroxide, and you'll see that as soon as that sodium hydroxide hits the solution, it turns pink. So, in the presence of a base, phenolphthalein turns pink. Okay, now we've got a tube here with some water. I've added another drop of phenolphthalein, and I'm going to add 5 drops of hydrochloric acid. So 1, 2, 3, 4, 5. So I've added 5 drops of hydrochloric acid. So this solution is filled with the acid. Now I'm going to start adding the sodium hydroxide. From your lecture, you should know an acid and a base, they're opposites of each other. So this hydrochloric acid should react with the sodium hydroxide. They react with and they neutralize each other. And there I've added a few drops, and oh, it still isn't basic. 1 more drop of the sodium hydroxide. Hey, now it's basic. Okay guys, on number 4 here it asked how many drops of the sodium hydroxide did it take to destroy the hydrochloric acid. Now we're going to do the same thing, but we're going to use sulfuric acid, H2SO4, instead of hydrochloric acid. So I got my water with the phenolphthalein, add 5 drops of my sulfuric acid. Now we're going to start adding the sodium hydroxide. 1, 2, 3, 4, 5 drops. Now, the hydrochloric acid turned pink after 5 drops. We've already added 5 drops to the sulfuric and it still hasn't turned pink. 6 drops. 7 drops. 8 drops. 9. 10. So it took 10 drops to neutralize the sulfuric acid. It only took 5 drops to neutralize the hydrochloric acid. Okay guys, we're on page 99 at the very top. It wants us to react copper metal with oxygen in the air. The copper metal is this shiny brown piece of metal, and to get this to work we need a good hot flame from our Bunsen burner. When we first turn the Bunsen burner on, the flame's not that hot. If we open up these little windows at the base, we let more and more air come in. More air coming in here gives you a hotter flame up here. Notice I'm not putting my hand through that flame. So now we have a nice hot flame, and we're going to take our copper metal, put it at the very tip of the inner blue cone until it glows red. It's glowing red hot now. And I'll take it out, and hopefully you can see it's no longer that shiny copper metal. It's now kind of black. And that black that you're seeing is copper oxide. So that's copper 2 oxide that's formed because it reacted with oxygen in the air. Okay, page 99, the second reaction is reacting magnesium metal. This is magnesium metal, very, very small, lightweight strips of magnesium. We're going to react those with oxygen. This is a lot more impressive than the copper. So, most people don't think of metals as burning in the air. Magnesium burns very hot and very bright. So here's my magnesium metal. We'll get it oxidizing with the air. And there's magnesium metal burning. Worth doing that one again. And there's magnesium metal as it's burning. Okay, page 99, number 3. The reaction of copper 2 sulfate with zinc metal. So here's our copper 2 sulfate dissolved in water. It's a nice blue aqueous solution of copper 2 sulfate. We'll add some of this to our test tube. And hopefully you're taking note of the blue color of the solution. We'll add in a couple of nice shiny pieces of zinc metal. That's zinc metal. We'll add a couple of those in there. And pretty quickly you should be able to see that the nice shiny zinc is turning all black. And we'll let that sit and react for about 5 or 10 minutes and then take another look at it. Here we are about 10 minutes later, and you notice all that blue color from the solution of copper sulfate is gone, and the zinc pieces are a decidedly dark black color. That black is due to teeny little dusty specks of copper metal. Now, copper is normally brown. Most metals, when you prepare them this way, when they precipitate out a solution, initially appear black. So that is our copper sulfate plus zinc metal. Okay, fourth one here on page 99 is the reaction of silver nitrate with copper metal. Here's my copper metal, these two shiny pieces of copper. We'll put them in our test tube there. And we're going to add our silver nitrate. If you're wondering, silver nitrate reacts with light. That's why silver nitrate is typically stored in an opaque bottle. You don't want it exposed to the light. It will react with the light. So we'll add our silver nitrate. You can see already how the copper metal is turning black. And that's because it's getting coated with silver metal. Hopefully you see that the solution starts out colorless. In about 5 or 10 minutes it should be a nice blue color. The solution should take on a blue color due to the copper 2 nitrate going into solution. So, about 10 minutes later, you can see how the solution's taking on that blue color. That blue color is due to the formation of the copper 2 nitrate, which is aqueous and dissolves in solution. And hopefully you can see some kind of granular silver at the base of the test tube. You may or may not be able to get a good view of that, but maybe you can see some of the silver metal down there at the, let's try and focus. See some of that grayish material. That gray material there is the silver metal. Okay guys, we're at the top of page 100 here. We're going to react magnesium metal again, but instead of reacting it with oxygen, we're going to react it with hydrochloric acid. what you should know is that a general reaction in chemistry is when a metal reacts with an acid, it typically produces hydrogen gas. So here's our acid, 3 molar hydrochloric acid. We're going to pour a little bit into a beaker here. And here's our strips of magnesium metal. And you can see it bubbling and fizzing. And those bubbles are bubbles of hydrogen gas. That's what we're making there, is the hydrogen gas. So the magnesium metal and hydrochloric acid, and in a very short time there will be no magnesium metal left. The magnesium's of course turning into the magnesium chloride. So acids, as advertised, they chew up and destroy and dissolve metals. And let's see, any magnesium strips left in there? One lonely one left. Okay, number 6 here. Potassium iodide reacting with chlorine, or Cl2. So, potassium iodide, we'll add some of that to our test tube, and as you'll see, it's a nice clear colorless liquid. So that's our potassium iodide solution. Potassium iodide is actually a white solid, but dissolved in water, it's a clear colorless solution. We're not going to use chlorine, the pure element chlorine. We're going to use chlorine water, so some chlorine dissolved in water. And as we add the chlorine water, you see how the solution starts to turn a dark color. That's because it is forming the element iodine, I2. So I2 gives the water that dark brown color. If it's concentrated enough, the solution starts to turn almost a purple, and sometimes you get little crystals of iodine floating around on top. Okay, our last reaction of the day. We're going to react ammonium carbonate. This is your ammonium carbonate, and we're just going to heat it up. As it heats up, it's going to decompose to form ammonia gas, carbon dioxide gas, and steam, which is H2O as a gas. So we'll start by putting a little speck of the ammonium carbonate into a very large test tube here. We're going to attach. Okay, here's our ammonium carbonate, and I'm going to affix some red litmus paper to the mouth of that test tube and start heating it. And as I heat it, it should decompose, giving us ammonia vapor. Ammonia is basic, and hopefully you saw how that red litmus turned blue, because the ammonia gas is a base. And if you take a close look, you can see how the ammonium carbonate itself is floating around real fast at the bottom of the tube. That's because it's turning into 3 different gases, and all of a sudden there's no ammonium carbonate left. It's all gone. It turned into water vapor, carbon dioxide, and